Periodic table. In this lesson, we're talking about what life was like before the periodic table, Mendeleev, the current periodic table, the elements, atomic number, atomic mass, valence electrons, metals, nonmetals, and metalloids, columns and families, and then lastly, rows and periods. Why is the periodic table important? Well, it's a useful tool for chemists. The periodic table organizes all the known information about the elements into a single place. Before the periodic table, chemistry was a mess. The elements weren't organized in any kind of logical way, and therefore it was difficult to find out information. Chemistry just didn't make sense. And then along comes Mendeleev in 1869 when he developed the first accepted version of the periodic table. He grouped elements according to their atomic mass, and as he did, he found that the families had similar chemical properties. His understanding was so advanced that he left blank spaces for elements he knew must exist but weren't discovered yet. And you can see an example of his periodic table right there. The current periodic table organizes elements instead by atomic number rather than atomic mass, as Mendeleev first thought. However, he was very close. The horizontal rows are called periods and are labeled from 1 to 7. So we have 1, 2, 3, all the way down to 7. And the columns are labeled from 1 to 18. And you can see they're going to go vertical, 1, 2, all the way to 17 and 18. And there's our current periodic table. Now the number up top here, that's going to be the atomic number. And you can see how it's going to go up as we go from left to right. And then as we get to the end of the row, it's going to start back over again. So 18 then goes back up to 19. One other thing you'll notice with the periodic table is that this section right here has actually just been removed from the periodic table. You can see it goes from 56 down to 57, from 71 all the way to 72. And then again, 88, 89, and then 103 goes to 104. So you can see this part of the periodic table can fit directly into the spots that were left open. The elements. There are 118 elements, 98 of which occur naturally. The remainder have been created in the lab, and usually only last for very brief periods of time. The universe as we know it is created out of these elements and nothing else. However, there may be elements that we haven't yet discovered. The periodic table. The periodic table organizes the elements in a particular way. A great deal of information about an element can be gathered from its position on the periodic table. For example, you can predict with reasonably good accuracy the physical and chemical properties of the element that you're looking at, simply based on where it is on the periodic table. You can also predict what other elements it will react with chemically. So let's start with atomic number. Elements are organized on the table according to their atomic number. The atomic number is usually found near the top of the square. It's not always found near the top of the square, unfortunately, as different periodic tables lay out their information in different ways. However, it's usually found atop. Sometimes it's top left, sometimes it's top middle, sometimes it's top right, but usually it's at the top. Now you'll be able to differentiate it from the atomic mass because it's going to be smaller. So the atomic number is going to be smaller than the mass number. You can see the mass number down here. The atomic number refers to how many protons an element of that atom has. No two elements have the same number of protons. If they did, they would be the same element. Atomic mass, on the other hand, refers to the weight of the element. It is found by adding the number of protons and the number of neutrons, and it's usually at the bottom, and it's the one that's going to be more than the atomic number. So mass is going to be greater than the atomic number. Atomic mass units, or AMUs. An atom's mass is measured in atomic mass units. It's so small you can't use things like grams effectively. There are approximately 6 times 10 to the 23 AMUs in a single gram. Each proton and neutron equal 1 AMU each. So if you have 1 proton and 1 neutron, your total atomic mass would be 2 atomic mass units. Electrons are only 1/2000th of an AMU, so we generally don't count them when we're doing our calculations. Valence electrons. The number of valence electrons an atom has may appear in the square as well. Valence electrons are the electrons in the outer energy level of an atom. These are the electrons that are transferred or shared when atoms bond together. Sodium, for example, has 1 valence electron. Fluorine has 1, 2, 3, 4, 5, 6, 7 valence electrons. Metals, nonmetals, and metalloids. Properties of metals. Metals are good conductors of heat and electricity. They're shiny and ductile. Ductile means they can be stretched into thin wires. Metals are malleable. They can be pounded into sheets, for instance. And a chemical property of metals is its reaction with water, which results generally in corrosion. Examples of metal include things like aluminum, gold, and iron. Properties of nonmetals. Nonmetals are poor conductors of heat and electricity. Nonmetals are ductile or malleable. Properties of nonmetals. Nonmetals are poor conductors of heat and electricity. Nonmetals are not ductile or malleable. Solid metals break easily. They're dull, and many nonmetals are gases. So you can see they're kind of the opposite of metals. And then you have metalloids, which are metal-like. They're similar to metals and nonmetals. They have properties of both. They are solids that can be shiny or dull. They conduct heat and electricity better than nonmetals, but not as well as metals. And they are ductile and malleable. Good example of metalloids include silicon and boron. Columns and families. Elements in the periodic table are grouped into 18 columns. So 1, 2, 3, all the way down to 18. Each element within a column or group contains the same number of valence electrons. So every atom in this column here will have 1 valence electron. Every element in here will have 2 valence electrons. It gets a little bit different when you get over here in what's called the transition metals. But when we get past the transition metals, we start to see our similarities again. Boron family is going to have 3 valence electrons. The carbon family will have 4. These guys will have 5, 6, 7, and this last group will have 8. So keeping in mind, the number of valence does not equal the column number, but everything in the same column will have the same number of valence electrons. The fact that they have the same number of valence electrons results in them having similar properties. They're going to react in the same way when involved with similar other kinds of atoms. Some of these columns are further divided into special families, Elements in each family have similar but not identical properties. So for example, lithium, sodium, potassium, and other members of family 1A are soft, white, shiny metals, and that includes all these guys except hydrogen. Hydrogen is not part of this family, even though it is inside group 1. It's inside group 1 because it also does only have one valence electron, but it does not have a similar characteristic to all these red guys right here. Hydrogen is in a class of its own. It's a gas at room temperature, unlike the metals underneath. It has one proton and one electron in its one and only energy level, and it only needs 2 electrons to fill up its valence shell. Alkali metals. The alkali family, these are the ones I was talking about before, are found in the first column of the periodic table underneath hydrogen. Atoms of the alkali family have a single electron in their outermost orbit. They are shiny, soft, and have the consistency of clay, and they react violently with water, and so are never found free in nature. Because if they were found free in nature, they would react violently with the water that's already in the air. Once they react, they wouldn't be found free in nature anymore. Alkaline earth metals. They are very reactive, but not quite as reactive as the alkali metals. They have 2 valence electrons, and they include things like magnesium, calcium, among others. You can see them outlined here. The transition metals are the metals you're probably most familiar with, things like copper, tin, zinc, iron, nickel, gold, silver, and for many, their number of valence electrons is variable, it changes. They are good conductors of heat and electricity, but don't all share the same properties, and this is mainly due to the fact that their number of valence electrons changes as you go within that transition metal group. The elements in the halogen family include things like fluorine, chlorine, bromine, iodine, and astatine. They have 7 valence electrons and are very reactive, therefore are also never found free in nature, just like our elements in group 1. And lastly, we have our noble gases, which are colorless gases that are extremely unreactive. They are inactive because their outermost energy level is full. They have 8 already. So they can only have 8 in the outermost energy level. They have 8. The family of noble gases includes helium, neon, argon, krypton, xenon, and radon. All the noble gases are found in small amounts in Earth's atmosphere. The one that you're probably most familiar with is helium, which is lighter than air, which is why it's able to float, as you can see here. And then lastly, we have our rare earth elements. The 30 rare earth elements are composed of the lanthanide and actinide series. They're mostly synthetic or man-made, and if you look at your periodic table, as we already discussed, you'll notice that they should fit right there. Rows and periods. Elements in the periodic table are also grouped into rows or periods. That's the same thing, so rows is going to equal periods. The periods are numbered 1 to 7, so you can see 1, 2, 3, all the way down to 7. Elements within a period do not share common characteristics, and this is because they have different number of valence electrons. For instance, potassium has 1 valence electron, whereas bromine has 7 valence electrons. So since the number of electrons in the outermost energy level is different, they're going to have different properties. You'll also note that bromine is a gas, whereas potassium is a solid. So they are very different even though they're in the same period. So before we conclude the lesson, I'd like you to watch number 2. Once you have watched the video, you'll have completed your lesson on the periodic table.